Before we dive into modern AI-based control methods, it's important to understand the foundations on which they were built. For decades, engineers have relied on a set of classical control techniques that have powered aircraft, industrial robots, autonomous vehicles, power systems, spacecraft, and countless other engineering applications. Each of these controllers was developed to solve different types of control problems. Some are simple and computationally efficient, while others are designed to handle uncertainty, constraints, or changing operating conditions. In this lecture, we will focus on five of the most influential traditional control methods. We will start with the PID controller, probably the most widely used controller in engineering. Next, we will look at the state feedback controller, which uses the system's internal state to compute the control action. We will then introduce the gain scheduling and appropriate that adapts controller parameters as the operating condition changes. After that, we will discuss H-infinity control, a robust control technique designed to maintain performance even in the presence of disturbances and model uncertainty. Finally, we will explore model predictive control or MPC, a powerful optimization-based controller that predict future system behavior while explicitly handling consistent. Although these methods may appear very different, they all share the same objective: designing a controller that enables a system to behavior in the desired way. So let's start with the most widely used controller in engineering, the PID controller. If you've taken a control systems course before, you've almost certainly encouraged PID controller. Despite being developed more than a century ago, it remains the dominant controller strategy in industry because of its simplicity, reliability, and effectiveness. At its core, a PID controller is a feedback controller. Everything begins with a desired value called the reference. This is simply the target we want the system to achieve. The controller continuously compares this desired value with the actual system output. The difference between them is called the error. If the error is zero, the system is doing exactly what we want. If the error is not zero, the controller computes an appropriate control action and sends it to the planet or physical system. The system responds, producing a new output. The output is immediately measured and fed back to the controller, where the comparison starts again. The continuous cycle measure, compare, act, and repeat is what makes feedback control so powerful. Rather than applying a fixed input, the controller is constantly adapting its actions based on the latest information from the system. In the next section, we will look inside the PID controller itself and see how it uses three simple components to generate this control action. Now let's look inside the PID controller. The name PID comes from its three building blocks: proportional, integral, and derivative. Each one answers different questions about the system. The proportional term looks at the present. It asks how large is the error right now. If the system is far from the desired value, the controller reacts strongly. As the error becomes smaller, the controller action is reduced accordingly. Next comes the integral term. Instead of looking only at the current error, it remembers the past. It continuously accumulates the error over time. This is important because even a very small error, if it persists for a long time, indicates that the controller should apply additional correction. The integral action is what allows a PID controller to eliminate steady state error. Finally, we have the derivative term. Rather than looking at the present or the past, it looks toward the future by measuring how quickly the error is changing. If the error is decreasing rapidly, the derivative term anticipates where the system is heading and begins reducing the control efforts before overshoot occurs. You can think of the three terms as working together. The proportional term reacts to where we are, the integral term remembers where we've been, and the derivative term predicts where we are going. By combining these three perspectives, the PID controller achieves fast, accurate, and stable control, which is why it remains one of the most successful controllers ever developed. The PID controller makes its decision based on a simple quantity, the error between the desired output and the measured output. For many engineering systems, that more than enough. But when if one measurement isn't enough to fully describe the system, consider a drone, a robot arm, or an autonomous vehicle. Knowing only the output doesn't tell us everything about what's happening internally. Uh, you may also need information such as position, velocity, acceleration, or other internal variables that describe the system's behavior. These variables are collectively called the state of the system. Instead of relying only on the output error, the state feedback controller uses the complete state vector to determine the control action. Each state contributes differently to the controller's decision. Some variables may be more important than others, so we assign each one an appropriate weight. These weights are collected in a matrix called the gain matrix, usually denoted by K. The controller combines the current state of the system with this gain matrix to compute the control input. This provides much greater flexibility than a PID controller, allowing us to shape the system's dynamics, improve transit performance, and stabilize complex multivariable systems. Of course, this extra capability comes with an important requirements. To use state feedback control, we need access to the system states or a way to estimate them accurately. As we will see throughout this lecture, that additional information enables much more sophisticated control strategies. So far, we've assumed that a single controller can provide good performance under all operating conditions, but in many real-world systems, that simply isn't true. Think about an aircraft during takeoff and landing, or a self-driving car moving from a highway to a crowded city street. The dynamics of these systems changed as their operating conditions changed. A controller that performs perfectly in one situation may perform poorly in another. Instead of searching for one controller that works everywhere, gain scheduling takes a different approach. It divided the operating space into different regions. For each region, we design a controller that is optimized for those specific conditions. As the operating point moves from one region to another, the controller automatically adjusts its parameters. In early implementations, this was done by switching between predefined sets of controller gains. Modern implementations goes one step further. Rather than switching abruptly, they smoothly interpolate between neighbors controllers, allowing the gains to change continuously as the system evolves. You can think the gain scheduling as giving the controller the ability to adapt its behavior without changing its underlying control strategy. The controller remains the same, but its parameters continuously evolve to match the current operating conditions. This makes gain scheduling a practical and widely used solution for nonlinear systems whose behavior changes across different regions of operation. Up to this point, we've assumed that our mathematical model accurately represents the real system, but in practice, that's rarely the case. Real systems are constantly affected by uncertainty. Sensors introduce noise, external disturbances influence the dynamics, physical parameters change over time, and no mathematical model is ever perfectly accurate. So the question becomes how can we design a controller that continues to perform well even when reality doesn't exactly match our model. This is the motivation behind the H-Infinity control. Rather than optimizing the controller for one ideal scenario, H-Infinity is designed for the worst case scenario. Its objective is to reduce the maximized effect that disturbances and uncertainties can have on the system. You can think of it as building a safety margin into the controller. Instead of asking how can I achieve the best possible performance, H Infinity asks how can I guarantee acceptable performance even under the most challenging conditions. This makes H Infinity particularly valuable in safety critical applications such as aerospace, autonomous systems, and industrial processes, where robustness is often more important than achieving perfect performance under ideal conditions. In other words, H-Infinity doesn't try to make the system perfect, it tries to make the system reliable. So far, every controller we've discussed has one thing in common. They react to what is happening now. Model predictive control takes a fundamentally different approach. Instead of asking, what should I do at this moment, MPC asks, what is the best sequence of actions over the next few seconds? To answer that question, the controller first uses a mathematical model to predict how the system will behave in the future. Rather than looking at a single instant, it simulates many possible future trajectories. For each possible trajectory, it evolves a cost function that measures how well the system follows the desired objective. At the same time, it must respect the physical limitations of the system. For example, an actuator cannot produce infinite force. A vehicle cannot exceed its string limits, and a robot joint cannot move beyond in mechanical range. These limitations are incorporated directly into the optimization problem as constraints. The controller then searches for the control sequences that provides the best overall performance while satisfying every constant. Um, Interestingly, also MPC computes an entire sequence of future control actions. It applies only the first one. A moment later, new measurements become available, the predictions are updated, and the optimization is solved again. This process appears continuously allowing the controller to adapt to change while always planning ahead. That ability to anticipate future behavior is what makes model predictive control one of the most powerful and widely used control strategies in modern engineering. So, we've now explored five of the most influential traditional control methods. At first glance, they may seem like a competing solution, but that's not how control engineers think about them. Each controller was developed to solve a different engineering problem. If simplicity and is our implementation are your priority, PID is often the first choice. When the complete system state is available, state feedback provides much greater flexibility in shape system dynamics. If the system operates under significantly different conditions, again, scheduling allows the controller to adapt its parameters accordingly. When robustness against disturbances and uncertainty is essential, HM-friendly control offers strong performance guarantees. And then future behavior and physical constraints must be considered simultaneously. Model predictive control becomes one of the most powerful available approaches. There is no universal best controller. The right controller depends on the system, the available information, the computational resources, and the designed objectives. Understanding these trade-offs is one of the most important skills in control engineering. So in the next videos, we will move beyond traditional control methods and explore how data-driven and artificial intelligence techniques are transforming modern control systems.